if you're dealing with spreadsheets on Microsoft Excel or Google Sheets and giving this two-dimensional input to, let's say, GPT-4, but when you try to ask questions from your spreadsheet via LLMs or GPT-4, it fails to give you appropriate answers. If this is happening to you and you're trying to understand why is this happening, or maybe you're a practitioner who's trying to solve this problem in your own unique use case or domain, or perhaps you are an enthusiastic AI follower who wants to understand, okay, does a solution exist? Is it possible in a non-mathematical, non-too technical way? Then you've come to the right place. My name is Hassan Ijaz, and today I will be going over the Spreadsheet LLM, which is an attempt to encode spreadsheets for large language models. It has been published by these great minds at Microsoft Corporation. The way we will go about this is we will directly study the research paper and go over the main highlights or details. And I've opened the actual paper and its appendix section on the right-hand side. The actual paper is on the left-hand side. Why? Because you will see in a minute or two why it's so important. Actually, let's start from the appendix section from the get-go. So you see, it's telling us why GPT-4 struggles to understand spreadsheets. And if I zoom in over here, you can see this is a conversation with GPT-4, and it's saying the following: that to understand a spreadsheet, you need some visual context. Like, it's giving a lot of visual cues such as cell formatting, colors, layout, etc. Then you also have within the cell some formulas or functions that are embedded into it. So it's not just looking at the raw numbers or values is not enough. They're even more complex because you can have cell references where you're linking different cells throughout your spreadsheet or parts of document. And then finally, you can have very huge spreadsheets which might be difficult for large language models to interpret or understand because they have a limited context window. And it has been proven that as the context window increases, the performance of the AI decreases as well. And then you can also have images, charts, pivot tables, etc. So that's why it's difficult to understand this information by when you give a table to the GPT-4. Now, to handle these challenges, of course, you could try giving an image, you could try giving the spreadsheet in a textual form to the GPT-4, but still it's not enough. When you talk about images, you need some contextual information about where the cell are, what are its addresses, more clear, compact information. You cannot do it using any vanilla approach. And what the author proposed is, let's take the spreadsheet and do something to it, some encoding and compression operation. And that process would allow us to have a better understanding of the spreadsheet. And then finally, you can, if you have that understanding, you can actually, when you ask a question, just extract the relevant parts of the spreadsheet and ask it questions. Now, it's a three-step process where we are encoding and compressing. It's a three-step process where we're trying to extract the table, then convert the extracted table into an encoded version, converting the table to a JSON formatting of sorts. And then finally, we are even considering the data formatting, because even that has some semantic or contextual information. We've looked at some examples and it will become clearer and clearer. So over here, we have the first step, A, B, and C. So you're seeing that it's basically trying to find the relevant tables, extracting the relevant tables. And if I can show you over here on the appendix section, these are all the different overlapping patterns of, these are all the different ways the table can be found. Of course, in spreadsheets, we can have lots of empty rows and columns. So this process just allows us to focus on the part which is most important. And once that is done, we try to encode the spreadsheet into textual form. So over here, we're using the markdown approach. So if you can pause the video here and look study it yourself. If I go over one example with you, you see it says A for El Dorado. So A for El Dorado. Then we have B for Quantum Mind, C for this, D for this. So this is basically going row by row and encoding that in Markdown. But this process is very inefficient, as you can see, because there are words that are being repeated, and we should not go about. We can make it better, and that better approach is called inverted index translation. So we are basically saying this word called subregion, it is being observed in A1 and F1. Is that the case? Let's see. A1 subregion, F1 subregion. So we see that's a way of encoding. When you look at quantum mind, so it's saying it's from B2 to B4, and then of course it will have where else it is occurring, we will continue in that fashion. You can see it over here as well. It's basically converting it into a JSON format. And then finally, we have the data format aggregation. We also looking at the formatting of the data. So for example, there is some year month data over here, D2 to D18, and then D21 to D23. So by using these three approaches, right? Structural, so we extracting, then we are translating, and then we are aggregating. These three methods allow us to do compression of the spreadsheet more quantitatively. This particular example, we had 567 rows and 23 columns. When we use the vanilla encoding method, which is using the markdown, we had 61,240 tokens. Tokens in this case means words. And then when we use the structural anchors, we go through the process of that is proposed by the authors. We are able to go to small 24 times 8 tables or sheets. And then, when you do index inverting and the further steps, you go through it. Finally, you go down to 708 tokens. So that's a lot of compression or efficiency over there. I can also show you some tables that give actual quantitative results. Over here, this is the mathematical representation of the steps I have just shared. You can go over them, in your free time. Actually, if time permits, maybe I can go over some of them with you as well. But right now, let's quickly jump into the results, or why you should be caring about this research effort. So in table 1, we can see that the total tokens are this, and the compress ratio is 1, and there is no compression is done. Now, as I said, we have 3 modules: extraction, translation, and aggregation. So module 1, 2, and 3. And we see as we add the modules, no matter which module you add, it sort of decreases the total tokens consumption. Now, how did we get to this compressed ratio? So that's this value divided by this value, and we get 4.41. Very logical, because if you divide this by this, you will get 1. So that's the normalization or compression ratio. That's how it's defined. And as we would expect, when you add all the 3 modules together, you would get the least amount of tokens, which is as follows. 24.79, that's the compression ratio. Okay, now, as we move forward, we would also like to understand, okay, for those who don't know, there's something called in-context learning, where you give an example of, okay, this is what has happened, and you give it an example and then ask it questions. So what we're doing over here is results of various model and method configuration on spreadsheet table detection. We want to detect the tables. And when we use just ICL, and you see, without any fine tuning the model, we notice the following. As you increase the size of the spreadsheet, the number drops down drastically. It's observed over here as well. But when you do use the compression method, then you see the table detection results are good or better than the raw one. But what if you were able to train the model, fine tune on this new approach? We see as follows. GPT-4 compress, when you do the compression approach and you use the GPT-4 model, you are able to get these accuracies. Overall, they're quite higher, much higher than the raw version. So basically, case in point, fine tuning helps, and this compression approach also helps. Now, a very important observation here is as you increase, as the spreadsheet size increases, so that's what this is: small, medium, large, huge, all. So as you increase it, you see the table detection just drops down to 0. Why is that happening? Because of the context window. Over here, we are able to go to 0.33 using the compress. But when you add fine tuning on top of it, you see the results is 0.69. There's the, if you remove the aggregation step, surprisingly over here, you have 0.753. That's the table detection accuracy. And the state of the art before this was table sense CNN. You can also see and compare its values over here. Now, the question is, why do we care about table detection? Well, firstly, as I said, you want to be able to deal with huge or large spreadsheets and be able to process them. And once you're able to do this, actually, let's make it a bit more concrete. And I'll just give you some examples. Well, firstly, when you talk about encoding, you don't have to do markdown. You can also do XML and HTML encoding. But as you can guess, it has lots of repeating tags, and that takes a lot of tokens. Therefore, it's not appropriate to use them. And Markdown is a better way to represent this two-dimensional spreadsheet input information. More quantitatively, this table 6 represents that information. These are the different encoding methods which are used to detect the table. We see on HTML, well, initially XML and Markdown start off great, but you notice as we go deeper and deeper and the spreadsheet becomes larger and larger, Markdown stands out. It performs relatively well. Why? Again, because of less tokens and being able to show the formatting in a better, more appropriate or concise way. So that's that. There's another table over here, and we can also go over it. But to understand it first, I also want to communicate another important concept, which can be found over here. So this is the markdown approach. We're going row by row. So B2, C2, D2, E2, so on and so forth. And you remember over here, so we were able to do this, but this has a lot of redundant information. But let's just look at 3 encoding values: XML, HTML, and Markdown. So Markdown is the best. And now let's use this best encoding that can exist, the Markdown encoding, and see what GPT-4 performs on it. What is its result on spreadsheet table detection with this cell formatting? We see that across all of them, so you can have the ICL. Just look at this, it decreases drastically as you increase the number of tokens or spreadsheet size. Then you can also have the fine-tuned version where you tell the model, okay, this is the markdown version of the spreadsheet. So again, it helps you to improve the performance, but you are unable to deal with huge or large spreadsheets. You could also include formatting into the encoding. What does that mean? So let's go back. It's over here. Perfect. So B2, but over here we're also including the formats. The font is bold. C2 is empty, D2 is empty, so on and so forth. B4, there's a bottom border. If you can have fill color as well. So you're basically looking at the formatting of the spreadsheet and also in giving that information. Surprisingly, when you include the formatting, because you're using too many tokens now, you're even unable to deal with medium-sized spreadsheets, and you could the same thing can be said for the fine-tuned one. Of course, you see the accuracy is high relatively. Yeah, it's higher than the raw version, but again, it's unable to deal with larger spreadsheets because of the context window issue. So we're talking about lots of different concepts. It will all make sense. We will go over it, revise it once I'm done explaining these individual components. So we've gone over this markdown. Those were the results shown over there. Now, as I said, we are trying to do table detection more concretely. Look at this image over here. So this is one table. This is the second table, third, and fourth. Now, if you use traditional spreadsheet understanding methods, usually they will miss the region R5 to R14. What is R5 to R14? So R5 to R14, this one. But because it has a numerical representation with this data over here, that is why we must include it. And this approach that we are using, the structural, the spreadsheet LLM, where we're using structural anchors, it allows us to do exactly that. Then we also have the concept about, okay, what does structural anchor-based extraction look like? This is another example. So raw data, like if you just give it to ChatGPT and predict the tables, this is what it will answer. You can pause the video here. I can zoom it a bit more for you and study that in your free time. And once you use the extraction method, you extract the relevant tables, which is this region over here and this region over here, and you remove everything in between and reassign the cell values. So that's your new table. So B2 to M20. Otherwise, it's like B2 to AK14, B2 to AK14, which is over here. And then you also have B19 to F25, this one. Now, once you have found the table, you want to ask some questions to it and get some answers. When you use the GPT-4 compress, the answers you see are answer accuracy is 0.743, which is the highest. And as you remove the individual components, extraction, translation, so on and so forth, you see the answer accuracy drops. The region, it represents the accuracy of predicting the relevant regions or relevant tables in the data, in the spreadsheet. When we have all the components, all three modules, then we accurately find the relevant spreadsheet values or contents with a 97.4% accuracy. Case in point, this works, it's important. And the spreadsheet Q&A, they've used a standard benchmark to use it. We can go over the detail a bit later. Next up, we have the inverted index translation. Without this translation process, the GPT-4 predicts as follows. So it's B1 to D14. Clearly, this is a mistake because they are two individual tables. This is one and this is the second one. But because they're combined together, GPT-4 is confused and unable to identify or separate the two when you use the translation method. So date is observed in B1 and then again in B11, B1 and B11. And because of that reason, it's able to understand, okay, this is header information, which is why it needs to be separate. And then lastly, we have the aggregation example. So it's saying B1 to C38. but you could represent this same thing, as follows. Now, because of this contextual information, we understand that, okay, previously it was like this, one value, and you're giving it an address, but over here we are talking about the format, right? So this is year, month, day, and then floating number. So that allows us to understand, based on the format, are we talking about the data, or is this some header information? What's going on here? Again, our goal is to encode the spreadsheet into a form that's easily understandable, and then we can ask it, we can give that relevance part to the GPT-4 and ask it questions. So that's the downstream task. And now, as you move forward, I've already talked about downstream tasks. Ask a series of questions: table question answering, table extraction, formula code generation, error detection, so on and so forth. And as I've said, LLM's token efficiency, that the performance of LLMs degrades significantly with long context. This is proven in these papers. And because of this, efforts have been developed to, for compression techniques for long prompts. This is one such attempt. This is the mathematical representation of the three concepts I just showed you over here. Among the three modules, the extraction module is a bit more, let's say, complicated. It has more steps. You can go over it in your free time. It demands some more respect. And then when you are asking or dealing with downstream tasks, you can use the chain of spreadsheet, where first, as I said, you identify the right table and its boundaries. So, where is it located? The top right corner, the bottom right corner, the top left corner, the bottom left corner. And then the query and the relevant table are input to the LLM, which allows us to give the answers. Now we very quickly go over the results. We've gone over these. It works. We are able to identify the table. You can see even open source models are used. You can compare between them as well. But case in point, the compression really helps improve the accuracy. You can pause the video and look at it. And when you fine tune it, it further improves the performance. You can see the real benefits of it when you have large spreadsheets. It's shown in this table 3. And you can see as you move to large spreadsheets, the raw, without any compression, you fail to detect the table at all. But as you have compression and use all the modules, you get the highest accuracy, so on and so forth. And as you sort of strip off the individual components, which is, that's why we call it ablation study, you see the accuracy continues to drop. Then we also have the Q&A results, question answering results. When you have compression and you also fine tune the model, you have a 0.743 accuracy, which is the highest. And it just works. Like all research papers, they're trying to communicate that this works, which is why we are publishing. Otherwise, we would not have. And so essentially what they have been able to do is deal with this two-dimensional input and communicate that they have a 22% baseline accuracy over GPT-4 model, and they have addressed this issue by identifying the relevant information or spreadsheet and only giving that to GPT-4. And this allows us to achieve a substantial reduction in token usage and computational cost. You can find that detail over here as well. Remember, it was 24.6% compression, and this allows us to perform better downstream tasks. Of course, there are some limitations. They can use better contextual and visual cues. They can also use, for example, China, America, France. They can have a unified label such as countries, etc. So this is what the paper is about. I hope it made sense to you. And if you have any feedback, comments, just get back to me. And that, in a nutshell, was the spreadsheet LLM. Thank you for tuning in. Have a great day.